Alright, so let's talk about localization. So for part A, we have a one-to-one correspondence. And I'm going to write this out. This is very important. Prime ideals. Here, I'm going to be really wasteful in my use of space, but whatever. So this symbol, I believe, is for one-to-one correspondence. So between the prime ideals of S inverse R and the prime ideals of R, which do not intersect S. And this correspondence, in one direction, it's pretty easy to see. You take a prime ideal R. If you take a prime ideal in R which does not intersect S, and you associate or you pass it through this map where you take all fractions of this prime ideal where the denominator belongs in S, then you get a prime ideal of S. And it turns out that this is a one-to-one correspondence. And so we want to describe the prime ideals in the ring of fractions S inverse R. So therefore, the collection of prime ideals in S inverse R can be, or is precisely the collection of all S inverse P, where P is a prime ideal of R and P intersect S is empty. Okay, so that's all that there is to part A, because that's how you describe the prime ideals in the ring of fractions. And because this correspondence is one-to-one, every prime ideal of S inverse R is given by S inverse P for some prime ideal P, and every prime ideal P, well, of course, prime ideal P which does not intersect S. And furthermore, every prime ideal P which does not intersect S gives us a prime ideal of S inverse R by this map. So that's all we need for part A. Then for part B, we want to use part A to show that there exists a prime ideal P such that F is not in P. So I'm going to actually do two proofs of this, I think. Right, because the proof that I'm going to do one proof that does one proof that actually uses part A, but it has a downside that some people might not like, and it's that it uses the axiom of choice. And so if I personally, I'm fine with axiom of choice. I think it's great. I think, yeah, you just throw it around. It's, yeah, whatever. But technically, I think you can do this without axiom of choice. And so I'm going to show another proof that has to do with that involves the nil radical and facts about the nil radical. And the I don't quite remember those proofs, but I don't think they involve the axiom of choice. And so if that is the case, then those proofs are technically a little stronger because you get the same result but with fewer assumptions. This is actually bugging me, so I probably should have looked at this a bit beforehand. But let's see here. I want to look up my exercises on the nil radical. You know what? Actually, I'm not going to do this now. This is a waste of time for you guys. So, anyways, I'm not sure if the facts about the nil radical do or do not use the axiom of choice. If they do, then if they don't use the axiom of choice, then it's going to give us a stronger proof, which does not follow the instructions, i.e., it does not use part A, but it's still a proof. But if it does use the axiom of choice, then, well, at least you'll see another proof. So now we want to find a prime ideal which does not contain F. Okay. So for part B, see here. Note that S is closed under multiplication and contains 1, because 1 is just f to the 0. And it's obviously closed under multiplication because, thus we can localize at S to obtain a ring S inverse R. And I think there's a technical detail of whether this S needs to include 1 in order for this to be localization. I think I've seen like different definitions. It's not. I don't think it's blatantly obvious whether or not S should or should not include 1. It might be obvious, but I think in general it's safe to assume that S includes 1. Well, actually, it doesn't really matter here because certainly we can localize at S. Well, I guess if you do need 1 to be in S in order to localize at S, then you do need to check that 1 is in S. Like, you do need to state that it contains 1. I think what it is I think that that people sometimes define at localization at S to be valid only when S is a submonoid of the multiplicative monoid of R, and by submonoid it needs to have that element 1. So i.e. you have S comma dot comma 1 is a submonoid of R comma dot comma 1. And so in particular this set S contains the element 1. And I think I saw it defined like that in at least one place. And maybe that's just a simplification to make the exercises and stuff easier. But the bottom line is we can localize at this S. And this gives us a ring SR. Now, by the axiom of choice, S inverse R contains a maximal ideal P. Okay, so actually, yeah, let's focus on this first. So how would this argument go? Basically what you do is you look at the collection of ideals of this holds for any ring. For any ring, you can use axiom of choice to prove that the ring has a maximal ideal. And what it is you look at the collection of ideals of your ring, which are like proper ideals, so ideals which are not the whole ring. And you look at this collection of ideals and you order it by inclusion. So, like one ideal is less than or equal to another one. Ideal 1 is less than or equal to ideal 2 if ideal 1 is a subset of ideal 2. And then what you do from there is you check the that every totally ordered subset has an upper bound. And that's true because to get the upper bound, you just take the union of all these ideals and it'll give you such an ideal. And then from there, you use Zorn's lemma, which relies on the axiom of choice, to conclude that you have a maximal element of this collection of ideals, of this collection of proper ideals. And so, yeah, by that argument, S inverse R contains a maximal ideal P. Then P is prime. And this is a basic fact about rings, is that maximal ideals are prime. And I think the proof is like a paragraph long or so, just a couple lines, and you basically do like a kind of an element wise argument. Like you take a maximal ideal and you suppose a product is in there, and you suppose a product is in there and you assume that one of the components of the product is not in there, and then you use that to construct an ideal which strictly contains your maximal ideal and thus is the whole ideal. And so then that will contain one, and then you use that to prove that the other element of the product actually is an element of your maximal ideal. That's like a very broad overview of it. It's not too bad, and you can work out the details if you want, or you could probably find it in some textbook. But maximal ideals are prime. And so this is pretty much what we want, right? Because by part A, P corresponds to a prime ideal P prime of R such that P prime intersect S is empty. So in particular, since our element F is in S, F is not in P prime. Hence, such a prime ideal P prime does exist. I.e., that means that we do have a prime ideal P of R such that F is not contained in this prime ideal. So there we go. That's the proof. If you're satisfied with that and you're fine using the axiom of choice, then that's fine. You can just stop there. But if you want to see another argument, then let's continue with that. For another argument, let's see here. So here, let P be a prime ideal. And this is of R. It should look like a hence. Anyways, so if the collection of Fn, well, if S intersect P is non-zero, i.e., so here S is the collection of F to the n's, so then Fn is in P for some n so here, if n equals 0, and I didn't really think about this. So if n equals 0, then 1 is in P, so P equals R. And then, what does that mean? So then we do have a prime ideal such that, we do have a prime ideal which contains, is that what we want? Sorry, I gotta look back up. There exists a prime ideal which does not contain F. Ooh, is this a problem? Oh, there might be an issue with this proof. That there exists a prime ideal which does not contain F. Right, because if what my argument says is that like f to the n is in P for some n, and then like, okay, you're assuming that n is greater than 0, and then you just have a product of like f times itself a bunch. And so this proves that f is in P. Oh, wait, this is actually what I'm trying to prove. So yeah, I think this works. So if n equals 0, then 1 is in P. So P equals R. And so f is in P. Okay. If n is greater than or equal to 1, then f is in P by primeness. That's because if n is greater than or equal to 1, then f to the n is just n multiplied by itself some number of times. And from here, use the primeness condition that, so if you have a product in your prime ideal, then one of the factors must belong to the prime ideal. But in this case, all of the factors are the same thing. Every single factor is f, and so f must be in P. Okay. Okay, so now assume for contradiction. So that's what we wanted to prove. We wanted to prove that if we have a prime ideal of R, then f is in this prime ideal. Wait. Does that even make sense? Anyways. Oh, right. Yeah, so for every prime ideal of R which intersects S, then f is in P. So instead of caring about whether or not this ideal, basically intersecting S is the same thing as having f as an element of it. Okay, so anyway, so this is all good. So now assume for contradiction that that for every, or rather that S intersects Pi for every prime ideal Pi of R. Then f is in Pi for all I. I belongs to some indexing set. I don't know how many ideals we're going to have. We could have finitely many prime ideals. We could have continuum many prime ideals. Who knows? But it doesn't matter. Because it doesn't matter, and so I'm not going to include, like, it's not going to be I and capital I where capital I is some indexing set. I'm just going to be kind of fast and loose with my notation and just use an index without telling you what the index belongs to. So anyways, so f is in Pi for all I. So f is in the intersection of I, Pi, i.e. f belongs to the nil radical. That's a fact about the nil radical. Here, actually, let me write out the rest of this argument and then go back and talk about the nil radical. But the nil radical, sure, I'll say the nil radical of R consists of the nilpotent elements of R. Okay, and so yeah, the nil radical, I believe the nil radical is defined to be the collection of nilpotent elements of R, i.e. the collection of elements of R such that you raise them to some power and it gives you 0. And you can prove that the nil radical of a ring is the intersection of all prime ideals of the ring. And so here, I want to say that proof takes like maybe 2 paragraphs, maybe a page, but it's sort of a standard fact about the nil radical. And so, yeah, so that's, if you don't know what I mean by the nil radical, that should be enough to where you can at least follow the logic of this argument. So the nil radical of R consists of the nilpotent elements of R. Thus, F is nilpotent, which is a contradiction. And so we have a contradiction from assuming that S intersects every prime ideal of R. And so because that leads to a contradiction, we know that there must be some prime ideal of R which does not intersect S. And let's see here. So it does not intersect S, and in particular, it does not contain the element F. And so there we go. That finishes our proof because so we have some prime ideal which does not contain our element F. And so let's see here, what else? Oh, the other thing I was going to say is this proof strictly better? Well, first of all, it doesn't contain, or it doesn't use part A. We didn't talk about localization at all, so this isn't what the question was asking us for. So, like if this was a test, which this problem was on a test, then this solution would be wrong. But in terms of being logically better because it doesn't use the axiom of choice, I forget all of the details of the proof that proving that the nil radical of R is the intersection of all prime ideals. It doesn't quite strike me as something that would require an argument by Zorn's lemma, because I cannot remember how it goes, that means that it might use Zorn's lemma. Like I can't guarantee that this can be proven without using Zorn's lemma. And if it is the case that this whole paragraph here relies on some fact that relies on Zorn's lemma, then this proof is no better than the other one. But if it doesn't rely on Zorn's lemma, then we've proven the same result using fewer assumptions, and so that's a good thing. That means we've done better math. But you can decide which one you like better, and if you were, of course, doing this on a test, you would want to use the first solution because that actually uses part A, and I would also use that because it's a lot faster. You just say, oh, there's a prime ideal here, so there's a prime ideal there. That's pretty much how the argument goes. So anyways, yeah, that's just about all there is to this problem.